Okay, so this is a review, theoretically, from last year. Okay, so we'll see how you two strap in. Okay, so magnetic flux. Okay, so just like electric flux is the area, the perpendicular area times the field. Okay, so they like this idea, like technically it's a dot product because they make the area of vector orthogonal perpendicular to that plane. I'm not a huge, I get it. The way I visualize it, I look at the amount, the component that's perpendicular, like perpendicular to the plane or of the area or perpendicular to the magnetic field, one of those two. Technically, textbooks write it as cosine because they look at this vector there. Okay, and it's in Weber's. So Lenz's law. This is the one where the induced current in a conducting loop will always be in the opposite direction of the change in flux. This is I don't know if you guys did this last year where you did this and then this or like this. We'll do a couple examples where you're doing the alternative right-hand rule. So the induced current always opposes the change in flux. You have Faraday's law, which says the induced voltage, the induced EMF, is equal to the rate of change of the magnetic flux. The negative sign is there because of Lenz's law. There's an opposition to that, and then N is just the number of loops. Okay. When you do this, so change in magnetic flux, you could be either changing the magnetic field or you could be changing the area. If you change both of those, which probably is not going to happen at this level, you would have to do the derivative in two different parts, sort of like the chain rule. I don't know what do they call that in math? We have two different variables that are changing. Anything? You haven't got there? Right. Do they call that? Do they have a name for that? Okay. Partial. Okay. So you leave one the same and take the derivative, plus you leave the other the same and take the derivative of the other one. Okay. So that. Okay. That's new. This you did not see this last year. You saw delta phi over delta t. Okay. So if we take this metal loop and rotate it, is magnetic flux changing? There we go to this. Yes, it is. The area is closing up. It's like no area there. Okay. Okay, I'm gonna run. I'm gonna do this as a straight example. Okay, ready? So we have a circular loop. We have a magnetic field going into the page. So therefore, we have flux going also into the page. Are we okay with that? The magnetic flux follows the same direction as the magnetic field. Okay, but what we're saying is it's decreasing. Okay, so check this out. Real simple example. let's say you have your initial velocity of 7 meters a second, positive. So that's going this way. Your final velocity is equal to positive 3 meters a second, going that way. The change in velocity would be equal to what? Be negative 4 meters per second going this way. Is everybody okay with that? Final minus initial. So we're decreasing the velocity. So the change in velocity is going this way, even though you're moving that way. There we go with that. Okay. So the magnetic flux is going into the board, but we're decreasing it. So the change in the direction of the change in the flux is going which way? Out of the board. Okay. The current that's induced in here opposes this change in flux, not opposes flux, but opposes the change in flux. The change in flux is coming out of the board. Therefore, the magnetic field that is created by this induced current is in opposition to this. So I stick my thumb in the direction of the magnetic field. The current is going around, in this case, clockwise. Okay, I'll run through that again. The flux is going into the page, but it's decreasing, so therefore the change in flux is coming out of the page. The magnetic field that is induced or created due to the induced current is in opposition to this change in flux. So my thumb is going to go in the opposition to this change in flux. This is the magnetic field that's created from this loop of wire with current flowing through it. Because it's been current has been created, it's going to go around that way. That is how you apply Lenz's law with your right hand rule. Okay. Thumbs up when you have a guess. Tell your neighbor. Correct answer is? Okay. So, field's coming out of the page. What's happening to the flux? Increasing, decreasing, or staying the same? We're decreasing the flux because the area is decreasing. So the change in flux is going into the board. The current that's induced in this loop of wire is in opposition to this change, counterclockwise. Okay, good. Tell your neighbor. Correct answer is A. Okay, super fast. You have to do normal right hand rule coming out of the page. So the magnetic field's going this way. The flux is increasing, so it's the change in flux is also out of the page. The magnetic field created by this induced current is in opposition to that, so it's going, thumb's going into the board clockwise. Tell your neighbor. There we go, C. There's no change in flux. Areas staying the same, magnetic field staying the same. Tell your neighbor. Correct answer is clockwise. We're decreasing the flux, so the direction of flux is going this way. The change in flux is going that way because we're decreasing it. Correct answer is A. Okay. Field lines are going this way. It's increasing because you're getting closer. So the change in flux is going this way. Magnetic field induced is in opposition to that. Thumb's going to the left. Correct answer, or tell your neighbor. Everybody good with E? Okay, when there has to be a change in the magnetic flux. Change in the magnetic field. Okay. There we go with D. Dangerous dinosaurs. Are we okay with C? Because we got more loops, more conductors experiencing a change in magnetic field. Oops, right there. 2 versus 3. Okay. All right, so you got Transformers have that ratio equation. Okay, so the voltage is proportionate to the number of loops. This is what gets the label stepping up or stepping down. It describes what happens to the voltage. Current is the inverse, is inversely related to the number of loops. Okay, because power has to be the same. So power in is equal to power out. Good with that? Conservation of energy. Correct answer is we go a step down. Has more loops on the primary than it does on the secondary. Tell your neighbor. Oh, wait a minute. You don't need that. Sorry. Forget that last picture. Correct answer is current decreases. You're stepping up the voltage, therefore your current is decreasing. Tell your neighbor. Here we go with C. All the electrons are along for a ride, moving charged particles through a magnetic field. Electrons are being forced down. Tell your neighbor. Correct answer is C. The electrons are being forced down here. So this creates your voltage, electric potential difference across this. So your electric field is doing out of positive into negative. Okay. Talk to your neighbor, have a conversation. Correct Correct answer is just A. Okay, sum of the forces are equal to 0. Okay, so in that case, that's a good place to start. Okay, so here we go. We're starting there. So we know that electric force is equal to the electric field times the charge. We know the magnetic force is equal to magnetic field times the charge times the velocity perpendicular. Okay. Good with that? Okay. Now we know that there's a voltage across that. Okay. So we're going to call that the EMF is equal to electric field times the distance. Right with that? Okay. And the distance here is going to be the length. So we've got the EMF over the length is equal to VV. Solving for EMF, you get that expression there. Good with that? Okay. Tell your neighbor. Everybody good with E? No, we're moving parallel to the magnetic field. No induced nothing. Tell your neighbor. Correct answer is bouncing buffaloes. Make sure you're using your right hand. Okay. All right. So looking at the simple model of a generator, you're pulling these through. Current, thinking about Ben Franklin, positive things are going to flow this way. If positive things flowed, electrons will go this way. Okay. So it's the same arrangement as this, except we've got rails and it's connected in a loop. So now we have current. We had voltage was induced always, but now we have a current. Sorry, we have a path for the electrons to flow. Now we have induced current. Okay. And so we've got this expression for how much current. We use Ohm's law, and here's our expression for voltage induced. So we can find our current. Okay. So in order to keep it moving at a constant velocity, as you're pulling this through, now you have current flowing through a conductor or a wire in an external magnetic field. you have current flowing through a wire in a magnetic field, it's going to experience a magnetic force. Okay, there I call it magnetic friction. Did Doc talk about that last year? So like when you are turning this, you want to participate? Okay, hang on to that. Sorry, you're probably be better off that way, right? You're right-handed or left-handed?
Right.
Okay, hang on to that here left. Okay, so I'm going to spin that just at a constant rate. I'm going to unscrew the light bulb and screw it back in. How would you describe the difference when it's screwed in versus not? It's harder when it's the current's flowing. Okay, you're good. Great job. Okay. So what we have is when current is flowing, there's this magnetic force that's opposing that motion. So from a junior high point of view, you would say you can't get electric energy for nothing. You've got to do work to make that happen. You can't get something for nothing. Okay, so as you're pulling through, there's this magnetic force. If you break the circuit, then there's no more magnetic force, and it becomes easy. Right with that? Okay. So if we're moving at a constant velocity, we're going to say these two forces are equal to each other. So the magnetic force is equal to the magnetic field times the length of the wire times the current which is flowing through that wire. And the wire specifically is meaning this thing here. Okay. So power is equal to force times velocity. We're moving at a constant velocity. Okay. So I can substitute that in for here. Okay. And pulling it. That was a big jump. What was I doing there? Current is here. Oh, that's what I did. Okay. So I substituted this in for current. And that's why I got all crazy complicated. That's where all the squares came from. Okay. And, or you can, this is way better. If you know the voltage and you know the current, you can just do that. Often they'll ask, what is the power dissipated? So you can either go that route or you can go that route. It's popular. This setup here, the simple model of the generator, is a popular free response stage. Just like the mass spectrometer where it goes in a circle is a popular free response stage. You can ask a lot of different questions with this scenario. Okay. Tell your neighbor. Correct answer is okay. Looking at this guy, this is the one that's moving. Thumb's going this way. Current is in the direction that positive things would flow into the board. Okay. Have a conversation. Okay. You're two people talking. Okay. Here we go. Everybody locked in? Committed? 20% chance. But you better get 20% chance. You better not just put nothing like, I don't know. Here's the deal. You're more apt to remember if there's an emotional response. So if you like are non-committal, like, oh yeah, I knew that. That's no emotional response versus like, okay. All right, here we go. This employs everything. Okay. So Lenz's law says we're increasing the magnetic field. So the magnetic flux is going into the page. The change in flux is also going into the page. The magnetic field that's created by the induced current is in opposition to that. So we've got current going counterclockwise. Okay, so we got current going this way, this way, this way, this way. Okay. On each part of this, I've got current going in an external magnetic field. It's being forced. This side's being forced down. This side's being forced to the right. And this side's being forced up. These two cancel out. There's no force over here because there's no magnetic field. So it's going to be 4 being forced to the right. I'm glad we're going over.
I was thinking like magnetic field increases, flux
Okay, I was following you until I used the last part.
Well, the flux is through the area. And
right.
If we pull it to the right, that's the way we decrease the area, which would cause a decrease in flux, which is opposition to the increase in magnitude.
Okay, you're not wrong.
Oh, okay. I'm basically perfect.
But if they ask which way is it being, well, I guess they did ask which way is being forced. Yeah. Have a conversation. Okay, what do you say? I should look for the question. I hear two A's. Everybody in agreement with A? Okay, so magnetic field's coming out of the page. As we pull it away, that strength of magnetic field is getting weaker because we're moving away from this wire. So the flux, change in flux is going into the page. So the magnetic field created is in opposition to that. So we've got counterclockwise. Right? Here we go. We I got something different than you guys got. Okay. The field is coming out of the page with this wire loop, right? Okay. So I've got out of the page. So circle with dot, dot, dot. Okay, I'm just doing that for showing magnitude. As we pull it this way, the magnetic field is getting weaker. Okay, so the change in flux is going into the page. Okay, the magnetic field that's created by the induced current is in opposition to this, counterclockwise. Good? Tell your neighbor. Explain to them how you got that. Correct answer is we got a vote for B. 2 votes for B. I got some shifty eyeballs and some nervous laughter. Okay, so current goes this way through a magnetic field that's coming out of the page. This one's being forced to the left. This one being forced to the right. Which one's so? Good job on B. Which one's bigger? Tell your neighbor. Force on the left hand wire or force on the right hand wire is bigger. Left. Big picture. Well, why? Because it's in a stronger magnetic field at that location. Big picture, there needs to be, if you're inducing current, there needs to be some net magnetic force that's in opposition to that motion. Good with that? Some magnetic friction, if you will. Do not put magnetic friction on the AP test. Okay. Tell your neighbor. They're okay with B. Okay, you can't get something for nothing. It's going to get brighter. There's going to be more magnetic force that's opposed to that. Next question. Everybody good with B? Bouncing buffaloes. Because there's two and there's two loops. Faraday's law. Hear that? Okay. Follow up. the sake of time, I'm going to lead you through this one. Correct answer is theoretically D, dangerous dinosaurs. Why? Because it has twice the resistance, because it has twice the length. Okay? It has twice the voltage, yes, but it has twice the resistance. Last question of the day. Conversation. I'm going to say true. Because even though the current's the same, there's twice as much length of wire experiencing a force. Therefore, it's going to, Newton's third law, there's going to be that same amount of force back on it. Due to that. So, was there anything